Okay, welcome back for part 3 of lesson 18 with the simplex method. So in the assessment you calculated d superscript y, and in this lesson we've already calculated d superscript x. The point of this is both of these directions, which we call simplex directions, are feasible. Okay, so we know they're feasible and they satisfy all those the properties necessary for that. So now we have to ask, well, we have a feasible direction. Now we need to figure out, is it actually an improving direction? Remember the big picture here. We're at x naught, x0, sorry. You can call it x naught, it's x0. And we have two directions now, dx and dy. And they're feasible. Are they actually going to help us get to optimality? Are they going to be improving? Okay, so because they're simplex directions, we actually know not only are they feasible, they are along the edges of the polyhedron. Okay, so both are on the edges of our polyhedron, which means that they point in the direction of an adjacent extreme point, or BFS for short. Well, BFS is short for basic feasible solution. The theorem says that that's equivalent to extreme point. Okay, so to do the improving direction, we're just going to use our gradient test that we talked about already. We're going to see if we're maximizing, is the gradient transpose D, is that dot product greater than 0? If we're maximizing, then it's an improving direction. Or if it's less than 0, then we're improving for a min. Okay, so we call this this calculation the reduced cost associated with a non-basic variable y when we compute this for a particular direction. Okay, why do we call it reduced cost? What we're trying to imply there is that this is sort of like the opportunity cost of adding the non-basic variable y to the basis. Okay, because if you think about it, moving in the direction of d super y means that you actually have to do different things to your basic variables. So for example, if we look at this d super x, right, for every unit, this is a unit of x that we add, we actually reduce the basic variables by this amount. Okay, and you can see, and I'm going to call it basic variable reduction or change. For this particular direction, that's a reduction. In general, it might actually be adding to those variables. It all just depends on the constraints and what basic feasible solution you're currently at for what's going to happen to the basic variables. I hope that starts to hint at you some of the possible things that could outcomes of moving in a particular direction. Anyway, so we take this direction and we're going to we have to figure out what was the costs. So the coefficient vector from the objective, and we take the dot product of that, and that tells you, well, what's the overall impact of moving in that direction. So we say that the simplex direction is improving if that reduced cost is positive for a max LP or negative for a min LP, and of course that's just the same thing as this condition. Okay. So we have I'm going to let you, I'm going to stop after this, and I'm going to let you, for the assessment, compute the dy reduced cost, and I'm going to compute the dx reduced cost. Remember, dx was equal to 1, 0, minus 4, minus 1, minus 3. Okay, right? That's what it was over here. And I get the cost vector. What is the cost vector? Now, when I look at this cost function, I might think, is the cost vector 13, 5. Of course, that's wrong. Why is that wrong? Well, you have to remember there's 5 variables, so you need all the other coefficients as well. So in fact, the cost vector is 13, 5, 0, 0, 0. I got this on my face. Okay, so I go back here, and I see that C is equal to 13, 5, 0, 0, 0. So the reduced cost, C bar of x is equal to C transpose D x, which is equal to 1 times 13 plus 0 times 5. Actually, let's write this in a way that is respectful of the order. So it's actually 13 times 1. It's not going to change the calculation. 13 times 1 plus 5 times 0. I just want to do it in the C, so it's C times dx, plus 0 times minus 4, plus 0 times minus 1, plus 0 times minus 3. And of course that equals 13, which is positive. And so, because the problem, let's see, were we minimizing or maximizing? We were maximizing. Okay, so because we are maximizing, this is improving. Okay. All right, so I'm going to stop there. You can see again, this condition is satisfied. I'm going to stop there, and for your assessment for, you please compute